Hello students, I hope all of you are doing good at home. I hope all of you are studying and welcome to a new lecture of physics, and today we are going to talk about diffraction of light. So in the previous video we discussed about Young's double slit experiment, and today is just a continuation of that. So today we are going to discuss about a new phenomena, that is diffraction of light. Now the first thing that comes to our mind when we read this topic is actually what do we mean by diffraction. Actually, what actually is this diffraction, right? I have heard this a lot, in our schools we have heard it, right? So basically, what is this diffraction of light, right? Okay, so in the previous video we studied about Young's double slit experiment, right? So in that experiment, actually showed us that okay, light does not have particle nature but it have wave nature, because we were able to explain Young's double slit experiment with the help of wave nature of light, right? Okay, so what we actually studied there, we actually studied, okay, that if we have two slits, right, it was something like this. Okay, uh, we had one slit like this, right? If you have two slits and if you have the screen, right? So what we studied that, okay, if the light is coming, like, let me say they're coming like the rays, right? If the light is coming like this, then if it had particle nature, then it would have straight away gone like this, right? And very similarly with the second slit also, it would have gone like this, and this is something which we would have expected. Here it should have been a bright spot, and here also it should have been a bright spot. Here also bright spot, here also bright spot, but here we were expecting a dark spot, and here also we were expecting a dark spot, here also we're expecting a dark spot, right? So this is how this is like we expected, right? But actually what happened, the same experiment, right? When we actually did the experiment, we came to know that at the center where we expected the dark spot, or I should say dark fringe, at the center we got a bright fringe, right? And we were getting this pattern, alternate dark and bright fringes, right? We call this we call this center one as central bright fringe, and then the dark fringe dark fringe, second bright first bright fringe, right? If you haven't seen the video, you guys can go back and check, right? So basically this is what we saw, right? This was the expectation and this is what we saw, right? So this proved, right, this experiment actually proved that light has wave nature, right? Light has wave nature, right? Okay, now we have to look very closely here. That what actually happened, right? So let me again just draw this. We had two slit in this experiment, right? And we had one screen, right? Yes or no? Right. Okay, great. Now when the light entered through the slits, right, right, our observation was that at the center, let me just, yeah, at the center we were able to see a bright fringe, right? Central bright fringe. So basically so if I just make it a ray version, so what I will see that through the slit the light would have bended like this. Yes or no? Light would have bended like this, right? Yes or no? Agreed, right? So in real sense we have studied that light always travel in a straight line. Okay, in our low classes we have studied that light always travels in a straight line, but here here when Thomas Young actually did the experiment, here we can see that light is actually bending. Light is actually bending. Can you guys see this bending here? Right there we can say light is bending, right? Light is bending, right? Okay, so this is very important observation over there, right? This bending observation was very important observation. So basically what is this diffraction of light? It's very simple. Diffraction of light is simply meaning that the bending of light, the bending of light around sharp corners, of obstacles. That is how NCERT says it. Obstacles or apertures is what is known as diffraction of light, right? So basically this bending, what we are talking, this bending of light, you guys can see this bending of light is what is termed as your diffraction of light, right? Okay, so now in the Young's double slit experiment we had two slits, right? Okay, again, what will happen if I had only one slit, right? If I had only one slit, so there's a very famous example. Okay, so what happened when we have only one slit? Okay, when we have only one slit, right? So basically again we will talk about two things here, right? When we have only one slit, okay, the light will pass through this one slit, right? Accordingly we should, we are supposed to get, if the light travels in a straight line, we're supposed to get a single bright spot or bright fringe over here at the center, right? This is something which is supposed to happen, but actually kya hota hai? Actually what happens, like I said, diffraction is the process of bending of light in the sharp corners, right? Sharp corners or sharp apertures, right? So basically what will happen in reality, what we are going to see is this is something which we expect, right? This is something which we expect. Okay, again remember this slit is very small, right? Very small. It is of, remember this is of the slits dimensions is of that of the wavelength of light. Very important, right? This phenomena is only observed when the wavelength of incident light is the order of the size of the obstacle's aperture. Very important, right? Very important. I'll just write it down as we go forward in the lecture. But actually what we are going to observe here is that, okay, if we have only single slit, normally we do this experiment with the single slit. मान लीजिए if you have if we have a source, the source will go in every possible direction, yes or no, right? So let's say the light rays are coming parallel here, right? So when the light rays are coming parallel, right, and if we have the screen here, so we have the screen here, right? So what we will observe is normally the light is supposed to go in a straight line, but as we saw here, it is going to bend. Light is going to bend, right? Normally we are supposed to expect this much bright fringe, but in reality we will observe this much bright fringe. And here also story does not stop, but after this bright fringe we will see dark spot, then again bright spot, and then again dark spot, right? Then bright spot. So basically you will see something like this. You will see at the center the bright spot, then on the other two side you will see dark spot, right? Then again bright spot, but this time the intensity will be much reduced. Then again dark spot, again a smaller dark spot, then again you will see a bright spot, but intensity will be much reduced. So basically what is happening, you will see this kind of pattern. This pattern is what you call as your diffraction pattern. Diffraction pattern, right? It is just like your interference pattern or your Young's double slit pattern, but the difference is in Young's double slit the the length, or it's just the intensity, remains the same, but here we can see that as we move forward the intensity is getting reduced of both, as well as for your bright spring it is getting faded out, right? We can take one more example here. Is let's say we have a source. I'll show you actually what it's going to look like, right? Let's say we have a source here, right? And we have a cardboard here, and through this cardboard, right, let's say you have a very small opening here, right? Although I have made it huge, look like huge opening, but it's a very small opening, right? So, and here is the screen, right? Let's say here is the screen, right? So normally this is something we are supposed to observe, ऐसे कुछ हमको मिलना चाहिए, right? But actually what happens, light actually bends, right? Right? So basically we will see a a, a bright spot of this much huge as compared to the the whole. You will see a much bigger bright spot, and then around it you will see dark spot, then again bright spot, right? Then again bright spot you will see, and then the dark spot, then again bright spot, and the intensity will keep getting reduced as the intensity will keep getting reduced as we go forward, right? So basically you guys, let me just show you guys what we will see. You will see something like this. I hope you guys can see this, right? So at the center you will see the bright spot, then you will see again after alternate bright spot, but as you can see, as I'm moving forward further, you can see the intensity is getting less, right? As we move forward the intensity is getting less. This is very important for you guys. So this is basically a diffraction pattern, right? I hope this will make you guys clear about the diffraction pattern, right? As you can see in this particular region, you can see the intensity of the bright fringe is much less. Yes or no, right? Why is that? Because we have moved a very far away distance from the center, but we can see at the center we will get the central bright fringe, right? Bright fringe. In this particular case we will call it central maxima. Right? In this particular case we will call this central maxima. I hope that is understandable, right? So let's go back here, right? So yeah, so I hope that is understandable to you guys, right? So again, very important point for you guys to notice. This phenomenon is prominent provided, this is very important point, provided wavelength of the incident light is of the order of the size of the obstacle's aperture, right? Very important point. The the wavelength of the incident light must be of the order of obstacles aperture, then only this phenomena you can actually see very prominently, right? I hope this is understandable, right? I hope that is clear to everyone, right? So let me just draw it, right? Let me just draw it, and let me try to make you guys understand what actually we are talking here, right? Okay, so let's say I have a source here. Let's say I have S source here, right? This source is a monochromatic source of light, right? This is a monochromatic source of light. This is a monochromatic source of light, right? Okay, so this is a monochromatic source of light. So what we'll do, we will put this monochromatic source of light. Okay, obviously monochromatic source of light, the the rays will go in all the possible direction, right? Okay, so basically what we will do in the experimental setup, right? This is the Fraunhofer experimental setup, right? So in this experimental setup we put a convex lens here, right? So this convex lens, all the light particle will strike this convex lens, right? Okay, let me just draw it like that, right? So all the light particles will strike this convex lens, right? Now you have to understand, this source is kept at the focus of the lens. It is being kept. So we all know, when light source is coming from the focus, after refraction it will go parallel to the principal axis, right? So that means all your rays will be going parallel now, right? All your rays will be going parallel now, right? Now what does that mean? It means that all the rays are coming. See, parallel rays means your rays are actually coming from a very, very far away distance, right? That is something which you have to understand. So parallel rays means we can very similarly say, or we can very comfortably say, that the light rays are coming parallel, right? Parallel, or I should say a very, very far away distance, right? Parallel beams means the light rays are coming from very, very far away, or I should say infinite. See, parallel rays very simply means the light rays are coming from infinity, right? We can say. So in order to make the light rays come from infinity, we put the source, the monochromatic source, at the focus of this convex lens, right? This is L1, and we call this collimating lens, right? We call this collimating lens, right? Okay, so we all know. And then we will be having the aperture. So this is the aperture here. See, I have made this aperture very, very huge, but you guys have to understand, aperture is of the order of the wavelength of the light that is incident on it, right? Okay, so it will come like this on the aperture, right? You have to understand, it will come like this. And we all know we are talking about wavefront here, so obviously plane waves will be coming, right? Yes or no? Plane waves will be coming just like that. Plane waves will be coming, right? And let me call the plane wave to be A and B, right? A and B. Plane waves are coming, and let me call the distance between the aperture, right? Let me call this distance. This is distance between your slit, or I should say the dimension of slit is A. Okay? Dimension of slit is A, right? So as we all know, what is going to happen? Okay, I forgot to make the screen. Okay, so somewhere here the screen is, right? Okay, so here is the screen. I hope you guys can see it, right? And let me make the center point. So here is the center point, right? So we all know what is going to happen. This AB wavefront is going to be incident on the aperture, or on the slit, right? So we all know, when it is incident on the slit, all the points here, there are a lot of, I can imagine this plane wave to be made of lot of points, right? Infinite number of points, or a very huge number of points, right? All these points will start behaving as the new source of disturbance, right? All according to Eigen's principle, all these points will start behaving as the new source of disturbance, right? So when they start behaving as the new source of disturbance, what will happen, right? Each and every point on this, on this plane wave will start emitting secondary wavelets, right? Will start emitting secondary wavelets, right? उसके बाद क्या होता है, we will actually in the, I should say, in the setup, there is one more collimating lens, right? In the setup there is one more collimating lens. Let me call this lens as L2, right? This is again collimating lens, right? So this lens, what is the work of this lens? This lens will focus, this lens will I should say converge all of your rays into the screen, right? This is the screen, so this lens will converge all your rays into the, that is the work here, right? So what is going to happen, we will actually see, देखो, normally we are supposed to, expectation is that we are supposed to see only this much bright fringe, right? But as we can see that the light actually bends, right? Light actually bends, so we will see more than that, right? So we will see this much central bright fringe, right? I hope everybody agrees with me. So this much central bright fringe we are going to see, that much, because there is a bending over here, right? There is a bending, you guys can see there is a bending over here, right? The light ray is supposed to bend over here, right? So we will see the central bright fringe, right? And after central bright fringe, what we will see? We will see the dark fringe. We will see the dark fringe, and then we will see the again bright fringe, and so on, right? So that is something which we are going to observe, right? So yeah, so this bright fringe is what you call as central. Say in the Young's double split we called it central bright fringe, but here we are going to call it central maxima. We'll call it central maxima, right? And we will call this first secondary minima. We will call it first secondary minima, and we will call this as again first secondary minima, and we'll call this as first secondary maxima. I hope, right? So maxima means we are getting a bright spot, minima means we are getting a dark spot. I hope you guys can follow, right? This is your first secondary maxima, right? So this is how we are going to see the pattern, right? So the pattern is somewhat like that, right? So at the center we are going to see a huge bright spot, right? More than what we have expected. And on the other two sides we will see alternate dark and bright fringes, and as we move forward it will be, the intensities of the bright spot will be keep on reducing. I hope this is understandable, right? So we will try to explain what is going to happen, what is the explanation for this central maxima, what is the explanation for your first minima, what is the explanation for your first secondary maxima. All right, so basically we can just write it over here, like your S is a monochromatic source, right? From here we can write it that S is a monochromatic source kept at the focus of this collimating lens L1, right? And what will happen? The emergent beam that will become parallel, right? That will become parallel to to the principal axis, right? We can say like that, and hence plane wavefronts AB, right? Plane wavefront AB is incident on the slit, right? Here is the slit and is incident on the slit, right? After, what is going to happen? Now the light is diffracted, which is focused on the screen with the help of lens L2, right? We have another lens L2, collimating lens L2. With the help of that L2, this light rays will be focused on the screen, right? And we obtain central maxima and alternate secondary minimas and maximas on its either side, right? I hope that is understandable, right? So we'll just try to explain like why we are getting this central maxima, why we're getting this minimas and maximas, right? So like I said, maxima means we are getting a bright spot, minima means we are getting a dark spot, right? So we can see it here. We have central maxima, we have secondary minima, then we have secondary maxima, right? So all these things we have, right? So okay, so let's try to understand, right? Let's try to understand the explanation of your central maxima, right? Okay, so let me just write it down. First thing, explanation of central maxima. So basically, why do you think we are getting this maxima, right? Okay, so let's get into it. Let's go deep inside, right? So here is the slit. Remember, we have only one slit. This is not your Young's double slit experiment in which we have two slits, right? Okay, so obviously incident wavefront AB, right? Incident wavefront AB will be incident over there, right, in the slit, right? Yes or no? So let's say this is the wave, or I should say the rays which are coming, right, which is incident on the slit, right? And then from there we will actually, the diffraction will happen, right? Okay, now so we can always imagine, like we discussed, we can always imagine this wavefront will to be made up of that lot of number of disturbing point, right? So let's say there are, for example, let's say there are 10 disturbances, just for example, right? So 1 2 3 4 5 6 7 8 9 and 10, there are 10 sources, right? And we just say at the middle we are going to see the maxima, right? So let's say this is the point, we call it point O, right? Okay, so basically what is happening in diffraction, what actually happening is that from single slit there are a lot of disturbances, right? And obviously every disturbance will emit a wavelet, yes or no? So let me say first disturbance will emit first wave, which will meet at point O. The 10th will emit again a wave which will meet at point O, yes or no? Very similarly, second will emit, okay, let me use different colors so that you guys can understand. Second will emit the wave, right? And ninth will emit a wave which will meet, right, again. Next, the third will emit the wave, right, and the eighth will emit the wave, and they're going to meet at O, right, and so on, right? So all of these, then the fourth will emit, seventh will emit, right, fifth will emit, then the sixth will emit, and they are going to meet. Now the important thing that we all have to see over here is, in all these emission, what is the path difference? Can you guys tell me what is the path difference? What is the path difference here? That is the important question I would like to ask. So in all these omission, right, 1 and 10, 2 and 8, 9, 3 and 8 and so on, right? In all these emission, we see, if I talk about BO minus AO, right? Normally we call it path difference, BO minus AO. Can I say the path difference is coming out to be 0? Very important thing which you guys have to understand here. Can I say the path difference is coming out to be 0? Yes or no, right? I hope it is understandable. Can I say that the path difference is coming out to be 0, right? So I can very nicely, I'm sure you guys can see that. Just take some time and just think about it, that in from all those sources, right, all those, I have assumed only 10 sources, there are a lot of sources. From all those sources, the waves are reaching, the wavelets are reaching the point at the center, right? And we can see, we know that at the center we are getting a bright spot, and we have studied in interference also, in Young's double slit also, right? So wherever there is, the path difference is coming out to be 0, or I should say n lambda, right, there is a bright spot, right? So path difference is actually coming out to be 0. So we can clearly see, so every point on the wavefront AV behaves as, so I can just simply, so I can write it down, right, like that, that every point on the wavefront AB will behave as the new source of disturbance, right? This is something which you know, right? New source of disturbance, right? New source of disturbance, right? And obviously there will be huge number of points, there will be huge number of points, right? Number of points which we have to understand here. There will be huge number of points, right? And they will emit secondary wavelets, yes or no? They're going to emit secondary wavelets, right? And we can clearly say from here, right, उसके बाद क्या होगा, right? And all of them will superimpose constructively, right? Now what does this mean, constructively? So basically we can see the difference BO minus AO is actually coming out to be 0. So constructively they will interfere, and what will, and we can very clearly see, and at point O, right, they will constructively interfere, and at point O, right, what we will see a bright spot, right? Bright spot, or you can simply say central maxima, right? I hope this is understandable, right? So you have to understand, this time we do not have two slits, we have only single slit. This is diffraction by single slit. So I hope that is understandable, right? So all the point will emit wavelet. So when we talk about 1 and the 10th point, 1 and the 10th point, 2 and the 9th point, so if I talk about the path difference, if I talk about at what difference they are, like, there is no path difference. If both the waves are coming at the same speeds, then obviously the trough and the trough is going to superimpose, and we are going to see a bright spot, right? I hope that is understandable. Okay, so after your central maxima, we are supposed to see what? We are supposed to see, yes, we are supposed to see secondary, yes, we are supposed to see secondary minima, right? So obviously, so let's try to explain, right? Now explanation to secondary minima means we are talking about the dark spot, right? So basically we have to now explain why is the secondary minima coming, right? Okay, so basically secondary minima means what? We're talking about dark spot, right? Okay, so let's try to redraw that again. Okay, so here's the screen will be there, right? Okay, so we know this distance is A, the distance between your distance, or I mean the, you know, how big your slit is, right? And from the center we can see, okay, so we know that our bright spot is going to be this big, right? Somewhat this big, right? This will be our central bright spot, right? Now after that we are going to observe, this is your secondary minima. This is your secondary minima, yes or no, right? Okay, so basically there will be a lot of points you have to understand here. There will be lot of points. So here 1 2 3 4 5 6 7 8 9 and one more point 10. So for time being, again I'm assuming there are 10 points, right? So you guys have to understand here, right? What I will do here, what I will do, we have to understand very carefully. I will do it, I will divide this A thickness by A by 2, right? So A by 2, A by 2, I have divided this into A by 2 and halves may I have divided it, right? So I have divided into halves, and obviously we can very clearly see the first wave is going to reach there, something like this. Let me call it point, this is some point P, right? Okay, all right, great. Then what is going to happen? Okay, then the 10th wave is actually going to meet there, right? 10th wave is going to meet there, right? And so on, right? And this kind of thing will, and we can clearly see from these 2 points that there will be some path difference, right? There will be some path difference, right? I hope that is understandable, right? There will be some path difference, right? I hope clear here, right? So let me call this point A and point B, right? Your A and B is the wavefront, and from there the wavelets are reaching your point P, yes or no? And we are getting a secondary minima, right? Okay, now all you guys have to understand here is, the thing that you guys have to understand is, see, when you have to understand, according the explanation for this is, the expression goes like this, and you guys have to bear with me and I'll tell you why is this explanation like that, right? We will say that all secondary minimas could be explained provided if we assume that path difference between the waves originated from the ends of the wavefront is integral multiple of lambda, right? Okay, now very important, okay, few things which you guys have to notice very carefully. See, if we assume the path difference between the wave originated from the ends of the wavefront is integral multiple of lambda, right? Okay, now the question to argue is, okay sir, lambda is, integral multiple of lambda means you're talking about n lambda, right? But we know that from Young's double slit explained that n lambda was supposed to be for your constructive interference, yes or no, right? But here we can see there is a minima, right? There's a destructive interference. Then how can you say n lambda should be there, right? So bear with me, I will make you guys explain that, right? So like I said, I have divided these 2 points, right? You guys can see I have divided into A by 2, right? Okay, so now you guys have to understand here, हम लोगों ने कैसे किया था इसको, if you guys remember, right? If you guys remember, we in the Young's double slit experiment, if you guys remember, let me just draw it again so and make you guys understand, right? So in the Young's double slit experiment, if you, जिन लोगों ने देखा है they might relate, and जिन्होंने नहीं देखा, you guys can go back and see. So it was something like this, and let me, right, so we used to say, okay, there is a wave from here, right, and the waves going from there also, right, and then from the mid there are this ray, and this angle is supposed to be theta, right, ऐसे हम लोग करते थे, and we used to say, okay, yes, the path difference is actually this distance, right, this was your m, right, so bm was supposed to be the path difference, right. So now, in according to my statement, I'm saying that from the ends it is actually n lambda, right. N lambda means, let's talk about, now this is your secondary minima, first secondary minima, that means the path difference will be lambda, right. So now very clearly you have to understand here, if this bm is lambda, then tell me what is this difference जो हाफ से आपका जा रहा है, will that be lambda by 2, right? Yes or no, right? So okay, now you have to understand, so I have divided my, if I had 10 disturbances, I have divided into 5 disturbances. 5 disturbance is for the upper part and 5 disturbance for the lower part, right? Now let's try to do this, right? Now let's try to do this. Okay, from the first the wave is reaching to the point P, right, and from the sixth, remember the second wave is going from the sixth, it is reaching, right. Okay, what is the path difference between first and the second? If the path difference between 1 and the 10 is lambda, then the path difference between 1 and the 6 will be half. Yes or no? That is, yes, that is lambda by 2, right. So lambda by 2, that means what? Destructive, right? Destructive interference, right? Destructive interference, yes or no? Very similarly, let's move forward. From the second the wave is going, from the second the wave is reaching there, and from the seventh the wave is reaching there, right. Okay, again, what is there? Difference between these two is lambda by 2, again destructive interference. Okay, let's move forward. From the third wave is reaching, right, from the third wave is reaching, and from the eighth wave is reaching there, right. Again, what is happening? Lambda by 2 is the path difference, again destructive interference. And finally, from the fifth the wave is going, and from the ninth the wave is going, right. So again, what is it? Again, we can very clearly say that there is destructive interference, right. So in that matter, in that way, we can actually make everyone understand what is actually happening, right. So from 1 and from 6, from 2 and from 7, from 3 and from 8, from 4, from 9th, and from 5th and from 10th, this is how you guys can make the understanding that why, although see, the waves are going in the pairs 1 and 6, right, then 2, second wave is going with your 7th wave, right, third wave is going with 8th wave, fourth wave is going with 9th wave, fifth wave is going with 10th wave, right. So there is the difference, the path difference is lambda by 2, again here also lambda by 2, again here also lambda by 2, right, again here also lambda by 2, again here also lambda by 2, right. So I have shown, I have make you guys understand by only 10 disturbances, but there will be a lot of disturbances, yes or no? There will be 100, 200, 300 crores of disturbances, right. So again, you have to divide those disturbances into two parts and make a pair like this, and all of them will do destructive interferences, right. So why I am assuming it to be n lambda, very important, I have used this term here, from the ends of the wavefront, from the ends, right. So when this destructive interference is happening, so when I talk about both the ends, end number 1 and end number 10, we will clearly see that the path difference is lambda, yes or no? Path difference is lambda. I hope that is understandable, right. So what we have to write, I hope that is clear. Just take a minute, take some time to just go back again and just try to understand that, right. Go back again, watch the video again, and try to understand. Just divide them into groups of 2, right, and then we can say if the whole group is having lambda, then the half of the group will be having lambda by 2, yes or no, right. And lambda by 2 is what? The destructive path difference, right? So that's why they will at point B they will destructively interfere, and we are supposed to see a dark, dark fringe, or you can simply say secondary minima, right? So overall we can say, we can say uh, we can say that from the ends of the wavefront, path difference, I should say, we can say that the path difference from the ends of the wavefront is integral multiple of lambda, right? Now we all know path difference is BP minus AP. Yes or no? Path difference is higher minus, so it is BP minus AP, and that will be approximately equal to your BM. Yes or no? It will be approximately equal to your BM, right? Just like we did in the Young's double slit, right? So BM will be approximately equal to, yes, n lambda. Yes or no, right? Again, your BM can also be written as a sin theta. I hope ये समझ में आ गया सबको. See, this is, let me use different pen. Okay, this angle is theta, right? This is 90 minus theta, right? And this angle is theta, right? So this will be a sin theta. I hope that is understandable, right? So a sin theta is there. So what will happen? This BM will actually be equal to a sin theta, right? Or you can say a sin theta is equals to n times lambda, right? This is how you can explain all your all your secondary minimas, right? I hope that is understandable. All your secondary minimas you can explain, right? Now the difference between your Young's double slit experiment and this experiment is that in Young's double slit experiment we had two slits, and here we have one slit, and from that one slit all your disturbances are interferingly, constructively, destructively, and we are seeing the pattern, right? That is the difference here, right? I hope you guys are getting what I'm trying to make you guys understand, right? Okay, now the next part, after your minima, then comes your secondary maxima, right? Then comes your next maxima, first secondary maxima, right? So explanation to all secondary maxima. So explanation to all your secondary maxima, right? Okay, so basically you have to understand here, right? You have to understand, again, same thing is happening. There is this slit AB, right? And there is this screen, right? Okay, and let's say okay, so this time I'm taking 9 points here, right? I'm taking 1 2 3 4 5 6 7 8 9, right? So I have 9 points, 1 2 3 4 5 6 7 8 9, right? Let's say we have 9 points, right? Now you have to understand here, right? And let's say this is the point P where your next maxima is coming, right? Your next maxima is coming. This is the point P where your maxima is coming, right? All right, so this is the center point, right? Okay, so this time I will divide this into 3 groups, right? I will divide this, so 1 2 3 4 5 6 7 8 9. You guys can see 3 groups I have divided it, right? Again, this is point A, this is point B. So this time, इससे पहले वाले केस में you have divided into 2 groups. This time I will divide it into 3 groups, right? Now you have to understand, the statement goes like this. Let me write the statement and then we'll try to we'll go into the explanation part. The statement goes like, all secondary maximas could be explained provided we assume that path difference between the waves originated from the ends of wavefront is odd multiple of lambda, right? Now what does that mean, odd multiple of lambda? That means your path difference is actually equal to, let me write it, 2n plus 1 lambda by 2, odd multiple of lambda. This is what odd multiple of lambda, where n will start from 1, 2 and so on, right? So basically iska matlab kya hai? If n is 1, the first comes out to be 3 lambda by 2, yes or no? And we all know 3 lambda by 2 is actually your destructive interference, right? 3 lambda by 2 is where we are supposed to find our second destructive interference, right? I hope you guys understand, right? Aapka kya tha? If you guys remember, 2n minus 1 lambda by 2, right? In which your first one was lambda by 2, right? If we put the value 2, it comes out to be 3 lambda by 2, the next one, yes or no? So 3 lambda by 2 comes under your destructive interference. I hope you guys remember that, right? So here I'm saying that you guys can get constructive interference with if you have 3 lambda by 2, right? Okay, now why I'm saying that, remember again I have used the term the waves originated from the ends of the wavefront is odd, from the ends of the wavefront, right? So remember I asked you that we have to divide this time into 3 groups here, right? In the previous one we divided into 2 groups, and the starting one we haven't divided into any group, right? So the second one, when we were explaining the secondary minima, we divided into 2 groups, right? Now here when I am explaining maxima, I have divided into 3 groups, right? Now when I divide into 3 groups, what does that mean? You have to understand. Now what does that meaning that I have divided into 3 groups, right? So now you have to understand that, okay, 3 groups mean 3 lambda by 2 will be the path difference for the entirety, yes or no? 3 lambda by 2 will be the path difference for the entirety, right? So let's say, okay, let's say from the first wave is going, the wave is going and it is reaching the point P, right? And from the fourth, the next wave is going and it is reaching the point P, right? Now remember, from the first and from the fourth, right, we can clearly see, if I divide into 3 groups, this will be lambda by 2, the path difference for the other next half is lambda by 2, and the path difference for the next half will be lambda by 2. So we can very clearly see lambda by 2, lambda by 2, lambda by 2. So from when your first wave is going from 1 and the second wave is going from the fourth, and when they are indifferent, the path difference between them is lambda by 2, right? So lambda by 2 is, that means there is destructive interference will happen, destructive interference will happen, yes or no? Okay, great. Okay, let's move forward. From the second the wave is going, it will reach point P, right? And from the fifth wave will go, it will reach point P, right? Again the path difference is, yes, path difference is lambda by 2, right? Again what will happen? Destructive interference will happen, the wave will destroy each other. Okay, next let's move forward. From the third, the wave will travel from the third, and yes, after third, from the sixth the wave will travel, right? From the sixth wave will travel, again the path difference is lambda by 2, and destructive interference will happen and they will destroy each other, right? Now is the important thing. Now we are left with 7, 8, 9, and there are no other waves which they should interfere and cancel each other. So this 7, 8, 9 wave is left now, right? So this 7, 8, 9 wave is very important, right? So this 7, 8, 9 wave will be shown in the screen at point P. They will be shown, and you guys can see there is this bright fringe. Why is this bright fringe coming? Because of this remaining 1/3 of the population of the disturbances, right? So 7, 8, 9, there is no other lambda by 2 wave which can interfere with them or which can cancel each other. So this 7, 8, 9 will come, right? They will come and it will be shown as the bright fringe, and we call that as your secondary maxima, right? I hope that is understandable, right? So basically what is going to happen, right? So one will come with the 4, or yes, one will come with the 4 and constructive lambda by 2, the path difference, they will destroy each other, destructive interference, right? Interference, and we'll see a dark spot, right? 2 will interfere with the 5th, again lambda by 2, destructive interference, right? Then 3 will interfere with the 6th, again lambda by 2 path difference and destructive interference, and this 7, 8, 9th one are left, right? They are left, right? They are left, and they will appear in the screen as the maximas, right? As the maxima, right? Very important, you have to understand. So I have told in the starting of the lecture that as we move forward, the intensity is getting reduced. Now you guys see, if you have 100% your light, so out of this only 33% is left, 66% they are cancelled out, right? So 33% will contribute to your bright spot, right? That's where the intensity will be reduced, right? I hope you guys can understand, right? Because only 33%, only you can clearly say यहाँ पे only 33% of the total are left. Total, okay, let me just rephrase that. Only 33% of the total disturbances will be left, only 33% of the total disturbances will be left, which will contribute as the bright fringe, or we can call it as maxima, right? I hope that is understandable, right? So because of that, we can see the intensity kept reducing as we move forward, right? So in general, I can write, so in general we can write that the path difference, that is BP minus AP, the path difference BP minus AP is actually equal to 2n plus 1 lambda by 2, that is the odd multiples of lambda, right? The odd multiples of lambda, very important, odd multiples of lambda. Here your n is starting from 1, 2 and so on, right? I hope that's understandable. And your BP minus AP means this will be approximately equal to BM, right? This will approximately equal to BM, and BM is equals to 2n minus plus 1 lambda by 2, or you can simply say A sine theta, that is equals to 2n plus 1 lambda by 2, right? Why it is A sine theta? Because as we can see it in the figure, right, this angle, again this angle is actually theta, this will become 90 minus theta, right? And this angle will become theta, and okay, this distance is your A, right? So this distance will become A sine theta, that is the path difference and throughout the end, right? Path difference throughout the end, right? And we can very clearly see that your A sine theta is equals to 2n plus 1 lambda by 2. So this is how you can explain your all maximas, right? All your secondary maxima, right? Okay, now very fast, let's try to find out the expression for the width of central maxima, right? Expression for the width for the width of central maxima, right? So let me very quickly find out the width of central maximum. So very clearly we can see this will be the slit, this will be the slit, right? Okay, so this is the incident AB wavefront that is coming, right? And this distance is actually small a, right? And let's say if this is the screen, we guys can see the bright spot will be something like this, right? Bright spot will be this bright, or I should say central maxima will be something like this, yes or no, right? And this will be your first secondary minima, right? This is again your first secondary minima, right? So basically I can very clearly say that the distance between, so this is your center point, let me call it the center point, the distance between your let me call this some xn dash, right? So if I'm able to find out xn dash, and if I double my xn dash, we will simply say, okay, now I know the width of central maxima, right? So it is very simple. You guys have to understand. So I'm sure you guys can understand this diagram now, right? Distance between the width of your slit is d, small a, right? The distance between the slit and the screen is, let's say, the capital D, right? And let me call this angle as theta, right? Let me call this angle as theta. I hope you guys can see, right? And this is the path difference, and this angle is also theta, right? So for first secondary minima, the condition we all know, the condition should be, let me call this point as P, right? Condition is that BP minus AP, that is the path difference, should be equal to your BM, right? Approximately will be equal to your BM, right? And we all know BM is actually your A sine theta, yes or no? So we can very clearly say, okay, yes, this is your BM, and BM is actually equal to your A sine theta, yes or no, right? And for first secondary minima, the condition is, it should be not for first, but yeah, for a general, the condition is n lambda, right? N lambda must be equal to your A sine theta, or I can say for the first, for the first, right, secondary minima, for first secondary minima, you will simply say the value of n is equals to 1. This will be lambda is equals to A sine theta, right? And we all know, and we know, as we saw in Young's double slit experiment also, that theta is very small, right? Theta is very small, the angle theta is very small, right? So that means your theta can be written as sine theta, can be written as tan theta, right? Because for smaller angles of theta, sine theta can also be written as your tan theta, and theta can be written as your sine theta and tan theta, right? So very clearly I can write it over here. This equation will change to lambda is equals to A tan theta, A tan theta, right? Now very important, let's go back here and let's look into this triangle, right? This triangle, the blue triangle that I'm drawing, I hope you guys can see. This angle is 90 degree, this angle is theta. So if somebody asks you what is tan theta over here, you will say perpendicular upon, yes, base, right? And what is perpendicular? Perpendicular is to your xn distance divided by base is your capital D. I hope everybody follow this particular expression, yes or no? So in that triangle, I can very clearly say that lambda can be written as A, yes, xn dash upon D, xn dash upon your D. What is your xn? distance between first secondary minima and central right fringe. I hope that is understandable, right? Okay, so that is what it is, right? Okay, so very clearly from here I can write your xn dash is actually equal to lambda d by small a, lambda d by small a, right? So this distance I know that is xn dash. So if you want to find a total distance, all you have to do is just double it. Yes or no? All you have to do is just double it, right? So the width of central maxima is w. Let me call it w. This will be 2 times of xn dash, or I can say w is equals to 2 lambda capital D by a, right? I hope that is understandable, right? I hope this is understandable, right? So in this entire lecture we talked about diffraction, right? I hope you guys understood diffraction of light. We try to understand, right? We talked about that what is diffraction. It's the bending of light at sharp edges, sharp obstacles, right? And we saw different examples, right? And then we tried to explain what is your central maxima, what is your secondary minima. We explained the condition, what is path difference happening in between, what is happening, what is the process that is going on, right? We try to explain, right? So I hope this lecture is understandable to everyone, right? So if you have any doubt, you can ask me on the comment section, no problem. I'll try to answer them, right? So I hope you understood the lecture. That's all for today's class. Thank you and have a nice day.